Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's class. In today's class, we will discuss a quantum mechanical operator that has great relevance in quantum mechanics. We are going to discuss about angular momentum operator. Before we discuss the quantum mechanical description of angular momentum operator, we will briefly see how we define angular momentum in classical mechanics and how we can write down its quantum mechanical operator form. We know that angular momentum is given by the vector product between the displacement and the linear momentum. The vector product between these two vectors r and p gives us angular momentum, and we use angular momentum to describe a system when a particular system is going in a circular path making an angular motion. So, therefore, the angular momentum becomes a useful quantity to describe the state of that system. When we try to find out the functional form of this angular momentum vector, we would know from the vector algebra. So, we write down I, j, k, these are the unit vectors along x, y and z axis. R vector has 3 components x, y, z. P vector, the linear momentum, has 3 components p x, p y, p z. When we look at this operation, then we can see that corresponding to I unit vector, I have I cap y p z minus z p y plus j cap z p x minus x p z plus k cap x p y minus y p x. So, this is what we get about the as the in the vector notation for the angular momentum. And here we see this part is essentially, since it is along I cap, we call this as L x, this part we call it as L y and this as L z. So, this is the x component, y component and z component of the angular momentum vector. Now, this is how we define angular momentum in classical mechanics. We know that when we discuss quantum mechanics, for every classical observable there exists a quantum mechanical operator. And since we have already defined the classical expression for the angular momentum, now we can define the quantum mechanical operator corresponding to that. So, when we write down the operator for Lx or Ly or Lz, we would simply use this displacement y, linear momentum pz. So, we know the position operators x or y or z, what their functional forms and how to operate them. We also know about px, py, pz, the linear momentum along x axis, y axis and z axis, what is its functional form and how we deal with them. So, we will use this definition to discuss the quantum mechanical properties of angular momentum operator. But before we do that, we first discuss what are very important properties of angular momentum is that they follow a particular set of commutation rules. We would first discuss what is the commutator between Lx operator and Ly operator. So, just to tell you, Lx, Ly, this is what we discussed just a moment earlier, how to write it in classical mechanics, and now we are going to write the quantum mechanical form of it. So, Lx would have y p z minus z p y, Ly will have z p x minus x p z. Now, we have y as an operator, pz is an operator, z, py, these are operators, and so each term in this expression is an operator. So, we can define this operator as putting a hat on top of it, but since there are going to be so many terms, for the moment I would skip using this hat. So, we just would remember that this y and pz, they are operators. So, now when I have to try to obtain one expression for this commutation, I see that I have to evaluate commutator between two products here and two products here, z p x, x p z. So, I can simplify this as y p z, z p x minus this commuter in the first line can be expressed as these four commutators y p z, z p x, and so on and so forth. So, I am first taking y p z and took the tried to evaluate the commutation of z p x, and then y p z with x, y p z with x p z, then z p y with z p x, and z p y with x p z. So, now this commutator I can evaluate by if I can evaluate these four commutators, but you see each of these commutator has A, B, C, D type of form. So, what I have here is that I have two operators here and two operators here. So, essentially I should know how to evaluate this kind of commutation. If you remember in a few earlier classes, in one of those classes we discussed how we can use this commutation, how we can evaluate this commutator when you have product of two operators are involved. So, in this case you remember, so consider that C D is a single operator, and I am first going to expand this A B product. So, to do that, so I have first A plus, now I would do for this we discussed in an earlier class. So, this is how we used when we have product of two operators and we have to evaluate the commutator. But still now we still have the C D operators which is actually the product of two operators, and now we would try to expand them. When you do this, this is the first term where I first evaluated the commutation between B and C by taking D out, and the second term will be when I keep C out and I evaluate the commutation between B and D. Now, I will look at this second term. The second term I first keep C out and then I would keep D out. Now, if I have A, B, C, D in this form, this is what I have to evaluate. Now, you see that now the expression that I have in this case I just have to evaluate the commutation between two operators B or C or B or D, A or D or A or C. Now, what we would do is that we would use this relation to evaluate the first commutator in this expression. So, the first commutator that we have is y p z, z p x. So, when you look at this, so this is my A is operator A is y, operator B is Pz, operator C is Z, operator D is Px. So, in this case I can simply write down A as Y. So, I am using this relation of this line over here. So, BC is Pz Z and D is Px plus AC, which is YZ, and I have to evaluate the commutator between Pz and Px, plus C, which is Z, and I have to evaluate the commutation between A and D, which is Y and Px. And now I have to evaluate the commutation between A and C, which is Y and Z, and D, B are Px, Pz. So, now when I look at this expression, I see that here I have commutation between Pz and Px. Since Pz depends only on Z component and Px has dependence only on x component. So, therefore, since these two variables have are defined in two different axes, so therefore, they commute with each other. So, this term becomes 0. Similarly, Ypx also becomes 0 because this is position along y axis and this is linear momentum along x axis. So, therefore, they are 0, and this commutation also, since it is y and z. So, this also becomes 0. Now, I have only one term here, which is Pz z. So, this we already have seen what is the commutation between x and Px, that was IH bar, and since this is the opposite of it. So, it is Px x kind. So, therefore, the value of this commutation is minus IH bar Ypx. So, here the commutator of Pzz is minus IH bar and I have Y and Px. So, this is what I got from the first term. Now, I would look at the second term, which is Zpy minus Zpx. So, instead of using this expression, writing down all the terms, we would just see which of these commutators survive, which of them do not. So, the first term, so we have A, B, C, D. Now, we will use this relation. So, first term requires a commutation between B and C. So, let us see what is B and C. So, Py and Z. So, they depend on two different coordinates. So, therefore, they commute. So, the first term becomes 0. What about the second term? B, D. So, Py, Px, they again commute, that is 0. So, again A and D. So, A is Z, D is Px. So, that is also 0, and AC, Z and Z. So, I have Z and Z. So, they also commute. So, Z we have seen the same operators, they commute. So, therefore, all the terms are 0. So, this expression is 0. Similarly, if we look at the third term, which is Ypz minus Xpz, we will find the first term Bc, Pz, excuse me. So, this should not be minus sign, this should be a comma, because we are trying to evaluate the commutator between Ypz and Xpz. So, we have A, B, C, D. So, first term will require the commutator between B and C. So, Pz and X, they commute. So, therefore, it is 0. The second term requires B and D. So, Pz, they commute, that is 0. Third term requires A and D, which is Y and Pz, they also commute. So, that is 0, and the final term A and C, Y and X, they also commute. So, therefore, all the terms become 0. Now, we have the final term, which is the commutator between Zpy and Xpz. We would see what we get from here. So, we have again A, B, C, D, we are going to use this particular relation. So, first term will require a commutator between B and C. So, P, Y and X, so they would commute. So, therefore, first term will be 0, second term B and D, P, Y and P. Now, we would look at the second term which requires a commutator between B and D. So, B is P y, D is P z. So, the second term will also become 0, and then the third term requires a commutator between A and D, which is Z and P z. Since Z and P z they do not commute, so this term will survive. So, we have to write carefully. So, we have C operator which is X here, the commutator between A and D. So, Z and P z, and then we have B which is P y. This, since Z and P z they do not commute, so this term will survive. Now, let us look at the fourth term which requires a commutation between A and C, which is Z and X. So, they again would commute and the term will become 0. So, I am left with the only one term, but I also know Z and P z they are their commutator, which is simply I h bar. So, I have I h bar x p y. Now, this is the term that survived here, and this is the term that survived in the first term. So, the overall, when I evaluate this commutator, so I am left with these two terms. So, when I simplify this, so I can write this, continue this discussion over here. So, I have I h bar x p y minus y p x, which is nothing but I h bar L z. So, this is how we had defined L z operator x p y minus y p x. So, we see that L x and L y they do not commute, that the commutator between L x and L y is simply I h bar L z. In the same way, we actually can write down L x, L y, they do not commute. So, this is I h bar L z, and L y and L z, I would encourage you to do it for yourself, so that you can practice how to use the commutation relations, and similarly L z and L x, that is I h bar L y. In our lecture, we derived this relation, but I would encourage you to try to derive these two relations. What we see is that the L x, L y, L z, the three components of the angular momentum operators, they do not commute with each other, but they follow a cyclic relation between them. So, this we will remember, but we would look at another commutator property. So, we have defined this operator L as L x, L y as having three components L x, L y and L z. Now, we are defining another operator L square, which is simply L x square plus L y square plus L z square. We would now try to find out what is the commutator between L square and L x. You see that L square is defined as L x square plus L y square plus L z square. So, therefore, to evaluate this commutator, I have these three commutator to be evaluated. Since I am trying to evaluate the commutator between L x and L x square, so I know in an earlier class we had discussed that a to the power n and operator a, they always commute. So, therefore, this term is 0, and I am left with L y square L x. So, this is a product of two operators L y and L y. To obtain this, I will have to have I will have to evaluate these two terms, and similarly when I evaluate this commutator, I have now look, the first term is anyway 0. When I look here Ly Lx, I know how they commute. So, you see the commutation with just now we derived Lx and Ly, the commutator between Lx and Ly is I h bar Lz. So, since this is the other way around Ly Lx, so it will be negative of I h bar Ly and Lz. So, I brought this I h bar minus I h bar to the left. So, this gives me Lz and this is Ly. So, I have Ly Lx again. So, minus I h bar Lz Ly plus I see the commutation between Lz and Lx. So, I know this is Ly. So, I h bar Lz and this is Ly, and then final term Lz Lx. So, that is again I h bar Ly Lz. So, now when you see Ly Lz with a minus I h bar, Ly Lz with a plus I h bar. So, these two terms cancel out, Lz Ly with I h bar, Lz Ly with minus I h bar. So, they cancel out, and now I see that operator L square commute with Lx. So, similarly, I can also show operator L square would commute with Ly, and L square will also commute with Lz. So, I would encourage you to follow this procedure and to show that Ly and Lz they commute with L square operator. We would continue our discussion and define one more operator from the definitions of operator that we have. We are going to define two new operators. We call that L plus operator, which is Lx plus I Ly operator, where I is the imaginary root, and we define L minus operator as Lx minus I Ly operator. So, these two operators we define now. We would show one important commutation relation. We will try to evaluate what is whether Lz and L plus they commute with each other or not. So, we see that Lz, so since L plus is defined as Lx plus I Ly, so I have simply and I know Lz Lx, when I evaluate this commutator, I get I h bar Ly plus I Lz Ly would be minus I h bar Lx. So, I see here plus I minus I, that becomes plus 1. So, I have h bar Lx plus, so this term I first wrote h bar Lx plus I h bar Ly, or I take this h bar outside and write it as Lx plus I Ly. So, these are all operators, but what is this operator? I have already defined as Lx plus I Ly is your L plus operator. So, this relation. So, Lz with the commutator between Lz and L plus is simply h bar L plus. So, I can also show Lz with L minus. You you should try to do it, and you would be seeing that this relation holds. So, what we have done is that we have discussed quite a few commutation relation among the angular momentum operators. Now, just to, since we defined so many new operators, so I would just spend a few minutes in discussing the summary of what we have done so far. We said that angular momentum operator, we can define the functional form of this operator by using the classical mechanical description, that L, the angular momentum, is the vector product between R and P. So, therefore, since it is a vector product, we have three components, Lx, Ly and Lz. We defined the Lx, Ly, Lz operator in these functional forms. So, where Py, Pz or Px, they are the angular momentum operators along y, z and x axis. X, y and z, they are the position operator along x axis, y axis or z axis. With Lx, Ly and Lz, we also showed that defined another operator as L square, which is Lx square plus Ly square plus Lz square. Apart from these four operators, we also defined two additional operators, L plus and L minus, in terms of Lx and Ly operators. So, L plus and L minus are simply positive and negative combination of Lx and Ly. Lx is in the real plane, Ly is in the imaginary plane. Given the definitions of these operators, we also discussed the commutation relations between them. We saw one important property is that Lx, Ly or Lz, they do not commute with each other, rather their commutators follow a simple cyclic rule. Lx and Ly would give you IH bar Lz and so on and so forth. While Lx, Ly, Lz, they do not commute with each other, what we discussed is that L square operator commutes with Lx, Ly and Lz. And finally, we also discussed another commutation relation where Lz and L plus will give me H bar L plus, and Lz and L minus would give, there is a typo here. So, it should be minus H bar L minus. So, just to refresh our memory, in today's lecture, we discussed about an important operator in quantum mechanics, the angular momentum operator. We spent quite a bit of time in understanding the quantum mechanical form of this operator and the commutation relations that it holds. I must remind you again that this angular momentum operator is a very important operator in quantum mechanics, which has wide range of applications. In fact, we would spend quite a few of our future lectures in discussing the applications of angular momentum operator in different chemical problems. We will continue our discussion in obtaining the eigenfunctions and eigenvalues of angular momentum in our future class. Thank you for your attention.